Now we're going to revisit the example for the RL step input, and again we're going to use this time the general first order response model to come up with the solution. In this example we have our 12 volt source that is not yet connected to a 1 ohm resistor in series with our inductor, and we want to determine how quickly the current through the system is going to change right after we close that switch and make that circuit completed. Okay, so we know from our general first order solution that we need to know three pieces of information. We need to know the initial condition, the steady state value of the current, as well as the time constant for the system. So let's start off with determining the time constant. The time constant we can determine by developing our differential equation model and putting it into standard form so that we're able to determine the time constant from that standard form. Alright, so as soon as this switch closes, we'll have the resistor connected to the inductor, and we will, since we're solving for current, we're going to apply Kirchhoff's voltage law around that loop. Alright, and Kirchhoff's voltage law tells us that all of the potential that's dropped across all of the elements has to be equal to the potential that is provided to the system by the input. Alright, so in this case, the 12 volt supply has to be balanced by the potential that's dropped across resistor 1 and the potential that's dropped across the inductor L1. Alright, and now we're going to use our current to voltage relationships to substitute, to rewrite these voltages in terms of current. Alright, so the current through all of the elements is going to be the same. I'll just call that I. And for the resistor, we know that the current to voltage relationship is given by Ohm's law, so V is equal to I times R1. We also know that the voltage to current relationship for the inductor is given by L times the rate of change of the current through that inductor. Right, and again, all of those are going to be equal to the input voltage after that switch has been flipped. Okay, we almost have our differential equation model. Let's put it in standard form by dividing through by R. So we'll have L1 over R1 times di dt plus the current has to be equal to the input voltage over R1. So now we have our standard first order differential equation model, and since it's in standard form, we know that this right here, what's in front of the first order derivative, defines our time constant. So we've found our time constant for this system. Now we need to set our sights on determining the final steady state value of current and the initial value of current. Alright, before this switch closes, this circuit is in an open state, and there's no current flowing through anything. So the time right before the switch closes, we know that the current through that inductor has to be 0. Alright, so before the switch closes, this inductor acts like a wire. There's no current flowing through the system, so there's no potential across the inductor or the resistor. So right before the switch closes, the current has to be 0. We know from the properties of inductors that the current through an inductor cannot change instantaneously. Therefore, right after that switch closes, the current through the inductor has to be the same thing as it was before the switch was closed. So that means that the initial condition, or the initial current through the inductor, has to be 0. After this switch has been closed for a long period of time, or as time approaches infinity, our circuit looks like this. We have our 1 ohm resistor in series with our inductive element, but as time approaches infinity, the magnetic field of this inductor becomes fully established. And we know from the properties of inductors that eventually that inductor is going to start acting like a wire. There's going to be no resistance to current, so we're going to have no potential dropped across that. So all of the 12 volts of potential that's supplied to the circuit has to be dropped across this 1 ohm resistor, which means the current, as time approaches infinity, is going to approach the voltage value, the supplied voltage value divided by the resistance, so V over R. So that means eventually this current is going to approach 12 amps. All right, so we have our time constant, our initial condition, and our final steady state value. And with this in hand, we should now be able to come up with the general solution for this step input case. The general solution for a step input to a first order system tells us that the variable of interest as a function of time is going to be given by the initial value minus the steady state value times e to the negative t over tau plus the steady state value. In this case, we know what these values are, so we're going to have 0 minus 12 amps times e to the negative t over tau. Since tau is L over R, that's going to be T times R1 over L1 plus our steady state value, which is 12. Okay. Rearranging this a bit gives us negative 12 e to the negative T times R1 over L1 plus 12. Or we could rewrite this as 12 times 1 minus e to the negative t times R1 over L1.